Okay, so I have a dream, and the dream is that I don't actually talk for that long. So, so we're going to see if you all pray, we might get somewhere here. Kristen actually did, in fact, mention at least 3 or 4 points from what I'm going to talk about. So I'm in that position of, of saying, oh gosh, she's already told all the jokes. So I'll just have to do the best I can. I've been told to be extremely careful about not assuming stuff. So what I'm going to try to do is give you a almost completely detail-free translation of what's an idea. And and I'm hoping that you guys, it's at a very preliminary stage. So I'm hoping to get some feedback from you guys. Okay, so first of all, let me begin with a philosophical remark. We've been talking about hard problems and not hard problems, and parameter sizes, and in most cryptographic systems, we've got a space. We've got some sort of space, and n is going to be the dimension of this space. And usually, and the question is, how do you pick it? No, it's not. Actually, it was 5 minutes ago, oddly enough. No, has anybody who's left-handed ever tried using on a whiteboard? Does anybody other than me feel that whiteboards are biased against left-handed people? because I think that they are. Alrighty, so let n equal the dimension of the lattice of the underlying vector space or lattice that you're talking about. And the question is, how big should you choose n? You need n big enough that it is hard to solve a lattice problem. It's hard to solve lattice problems. In other words, it's hard to solve a closest vector problem. It's hard to solve a shortest vector problem, something like that. And people are getting painfully insecure these days. So back in the early days of knapsacks, people used to think, well, 100, did n equal 100, ought to suffice. And then one of the people in our front row was a perpetrator of an LLL algorithm, which made a lot of these knapsack systems go out the window because, well, n equal around 100 just didn't cut it anymore. And then about 1996, when we were first starting to do NTRU, the interesting situation was nobody actually had the faintest idea of what of how effective lattice reduction techniques were. LLL was new then. I asked one of the people who actually invented LLL just exactly how effective that was as the dimension went up, and that person responded, "How the heck am I supposed to know? I'm a theoretical mathematician." I don't know if you remember that.
I would still say the same thing.
It was in Berkeley. It was in the spring of 1995. I remember. I was curious about that thing. Anyway, so and that turned out to relate to a whole lot of strange things because when NTRU first got created, the ends were on the order of, well, and here's we get difference between dimension and parameter size. So first, if n is the dimension where it's hard to do something, then for standard lattices, it takes on the order of n squared bits, really n squared log n or n squared log log something, but roughly on the order of n squared bits to describe a lattice. And so if you're in but the situation with NTRU was that n was the dimension, n was actually equal to the degree of a polynomial, and we were taking n to be At the very simplest, the very bottom of the barrel case that we were taking was n equals 167. I'll tell you what all these numbers mean, what they're attached to in just a moment, but I just want to give some gestalt here. We had originally n equals 167. That happened to correspond to 167-degree polynomials. It happened, however, to correspond to a lattice of dimension 2n. So that was the tremendously convenient aspect about of the way n-true worked when we were first doing it. Your parameters were just on the order of n, but the lattices bumped you up even higher. So if you take n equal to 167, then that was, assuming I'm getting this right, then that corresponded to a lattice of dimension 334. And actually, in 1997, Joe and Jill and I posted a couple of problems a couple of challenge problems involving lattices, and there was one warm-up problem where n was 103, and over the years, 2 people solved that. 167, it's been since 1997. Nobody solved that one. That is a mere 334-dimensional lattice. That's peanuts in today's world, where people get tremendously nervous if the dimension of the lattice is under 2,000 or so. So there's a certain disconnect these days about what is really hard in terms of solving lattice problems and what's not tremendously hard in solving lattices. And of course, in cryptography, you've got to be conservative. But I wonder occasionally if people are just the tiniest bit too conservative these days in estimating how hard lattice problems are.
The reason of a lot of crypto systems getting larger dimensions is that they need a larger gap.
And the main reason, yes, the main reason why the dimensions get so big is because there's a parameter q, which we've heard of. There's a parameter q, and as this parameter q gets enormous compared to n, the ease of solving the associated lattice problem gets simpler. That's how I think, and that's connected with you mean about the gap. I mean the sparsity of the.
For n-true lattices, there are abnormally short vectors. For L will be as well, and yes. How large this gap is drive the security. So it's not surprising that for some other application than encryption, you need larger dimension than 167.
No, it's definitely not surprising. All I'm saying is that I think the tendency has been a tiny bit extreme. But people are paranoid, and rightly so. So it doesn't really matter. Anyway, but I'm mentioning this because what I'm trying to get at today is I would like to find what I'm going to present to you today is an idea for a system where parameters are on the order of n, some n, and the associated lattice, and I'll tell you what an associated lattice is. The associated lattice has dimension on the order of n squared. And so that has the potential to make things a whole lot easier to compute. You want to work with n as small as possible, consistent with having your lattice dimension as big as possible. You want that, and so the reason for what I'm proposing, for what I'm going to be mentioning to you, is this theoretical aspect. Okay, so and what I'm telling about is it's joint work so far with just Joe Silverman, and though probably a bunch of other people will join in because it's fun. So what do I want to do? How do I want to describe this? Well, here's the basic object, the basic tool in n-true or any one of these polynomial type lattices is as polynomials of the form. Say you've got an a of x is equal to an a0 plus a1x plus a sub n minus 1 x to the n minus 1, and suppose you've got a b of x, and that's the same thing, b sub n minus 1, x to the n minus 1. And suppose that these ai's and bi's are drawn from a pretty restricted range. Suppose they're just allowed to take on the values of 1, 0, or negative 1. Then if you do something like this, then I label this short, okay? So A and B are referred to as short vectors because the norm, because the L2 norm of these vectors is on the order of the square root of n, and the L infinity and the L infinity norm of these is like a constant, and a small constant for that matter. Okay, and then the key point: what does it mean in n-true? In n-true, we work in. Whoops. In n-true, we work in z of x, we work in z mod qz of x, modded out by x to the n minus 1. And what that means is that when we define a of x and we do the ring operation a of x times b of x in this ring, then what we get is actually the genuine polynomial a of x times b of x plus some other random polynomial, we don't know what, times x to the n minus times x to the n minus 1, and then this whole expression is reduced mod q anyway. And so, and when we say, and if a of x and b of x start out being short, then this L of x is going to be very short too. And this, the polynomials are going to go into the coefficients of this polynomial are going to be reasonably small. And the general rule is that short times short is, well, pretty short. Okay, to invent a suddenly new technical term. Okay, so short times short is pretty short. That's what the whole crypto system is based on. And in particular, it's based on the fact that if you've got really small coefficients mod q, but if you have really small coefficients absolutely, and you multiply one short thing by another, none of these coefficients are going to get big enough to go over q over 2 or below minus q over 2. Now, if n was gigantic compared to q, that wouldn't be true. But if q is bigger than n, the chances are pretty good that no reduction in mod q is going to take place when you multiply these things. So that's the basis of this. And it turns out that this business of short times short equals short doesn't just happen in this context. And so what I'd like to show is what I want to talk about is an example where say f of x is I don't know, let's call it a, as usual, let me just call it a0 plus a1x plus a sub n x to the n. I want f of x to be monic. I want it to be degree n. I want to pick a q, which is in fact a prime. And the question is how big q needs to be. Well, that remains to be seen. So I want to take f of x, this, I want monic degree n, and here the a0, a1, etc., chosen once again from ones or zeros or negative ones. And the claim is that it is once again true in this context to find I want to work in z of x modded out by the ideal f of x, the ideal generated by f of x and q. Or in other words, what I wanted to work on is z mod qz of x modded out with the ideal f of x. And so and so by multiplication of two things, I would mean that if I pick an A, and let me just call this R, okay, or let me call it R sub f. If I take an A and a B inside of R sub f, and A and B are short, then here is the not really surprising fact, then A times B is also pretty short. That's not at all clear, really, why it should be the case. And if I were doing a slide presentation, I would show you table after table, giving evidence for this thing. So why don't you just assume that I've just showed you table after table of massively mounting evidence that this is the case. It turns out, well, it's true to some extent. Basically, if you start with if A short and B short means that if you compute A of x, if you compute the product in this ring, computing the product in that ring is going to mean actually multiplying the two polynomials A of x and B of x, and then subtracting off whatever is a necessary multiple of f of x to get every degree down below n. So you do that times that is this minus this, and my claim is that if f consists of 1s and minus 1s and isn't too big, then L of x doesn't have big coefficients either. And the product of these two doesn't, and this times this doesn't, and as a result you have the short times short is reasonably short thing going on. So if you accept that, then I will then I'll move on. Okay. So what I want to do now, is I want to do this twice. So now I'm going to just explain. I'm going to explain a crypto system to you. So I'll be very careful. The public I actually have a green marker and a red marker. I was about to say I'm going to mark the public stuff with black, but I'm going to mark the private stuff with black because they both start with the same letter P. So let me. And I already know as a fact, well, okay, I'm going to make a pitiful attempt to keep track of public and private with green and red. I have very bad feelings about this. So here we go. I want to pick, here we go. I want to pick f of x. I told you it's going to be bad. I'm just going to stick with black. I'm going to pick. I suffer a certain amount of dyslexia when I'm talking at the board, and the word that I'm about to say 3 words in advance turns out to be the word I tend to write. And if I add to that the problem of choosing between green and red markers, I don't even want to think about what would happen.
So I should have said it's okay for you to use slides when you were asking me. If you have slides,
no. I hate slides. I actually really hate slides because information goes by really fast, and when you're sufficiently incompetent at the board, information goes by sufficiently slowly that people have a chance of absorbing it, I hope. So here we go. What I want to pick f short. I want to pick f consisting of with coefficients from 1, 0, minus 1, and I want f to be monic. Well, of course it's I want to say monic degree n and irreducible mod q. So q. So let me just list them up here. So n and q are going to be public. Everybody knows what that is. F is private. I want to pick a public thing, H, with coefficients are general mod Q. Okay. So NQ is public, H is public, and the degree, and H is also monic, irreducible, degree n. Okay, so now this gets back to the point that Kristen was making about different names for different fields. If we consider Z mod QZ of X.
So irreducible modulo Q.
Introducible modulo Q is what I mean. Yes. So if you take Z mod QZ of X and you mod it out by the ideal generated by f of x, you get something which, of course, is isomorphic to the one and only finite field with q to the n elements. On the other hand, if you do exactly the same thing with H, if you get this is also isomorphic to Z mod QZ of X modded out by H of X. So for a long time, I wondered if it was possible to build some sort of homomorphic encryption type thing, and I realize that hasn't even been discussed yet so far, so I'm going to actually tell you what I mean by that in a moment. But I often thought it would be great if you could do something like that using isomorphisms and finite fields, but I basically thought finite fields are so terribly boring. There's only one of them. How could you possibly get sort of something interesting going on? But I think there is something actually interesting going on because there's an isomorphism going from here to here. And that's a very subtle thing, actually. And this isomorphism will work like this. X, and I'm sorry, oh no, I meant to do this ZQ of X mod H of X, but we will be terminally confused unless I refer to that as Y. Okay, so believe me, we need to do this. So I'm gonna refer to this as the Y space. I'm gonna refer to this as the X space. So these are both n-dimensional vector spaces over Q. They happen to have a multiplicative structure. They happen to all be isomorphic to the finite field with Q to the n elements. And if you take X, start over here, and map it over by this isomorphism, it's going to land inside of the Y space. Now, everything in the Y space is a polynomial in Y. So I'm going to say that X is going to map to phi of Y inside the Y space. Okay, and now, and then there's an isomorphism, and there's a reverse isomorphism. Y will map back to a psi of x. And the nice thing is that you could pick F and H completely separately. They have nothing whatsoever to do with each other. It's always possible and relatively easy to construct the associated maps phi and psi. So I won't get into that. So you could do this. It's not a problem. Now, how do you want to use this? Well, I'm sorry? I still psi of it. What? Y is going to Y is going to get mapped to it's going to get mapped to some to some polynomial on X, and that's what it has. I'm just naming it, and you can find out what these things are explicitly. All right, and now what I want to do is I want to describe a way to encrypt. It's going to be pretty boring at first, but the nice thing is going to be that it's actually possible to a certain extent to multiply this, to add and multiply this encryption function. And so here's what I'm going to do. I'm going to start with M, and suppose M, I want to be very specific here. I don't want to say you could take some random encoding of M, but just to be extremely specific, let me say that, for example, M has a base 2 expansion, like the M0 plus 2M1 plus 2 squared M2 plus 2 to the n minus 1 M sub n minus 1. So then what I want to do is I want to map M to the polynomial M of x, which is M0 plus M1 of x. M0 plus M1x plus M2x squared plus ... And so I'm encoding M, saying if I take this polynomial, if I substitute x equals 2, I get the value. So in other words, mod, so what that's saying is that mod is that M of x mod x minus 2 is equal to the thing we're interested in, M.
Does the n in there include the n minus 1 have anything to do with the f to start with?
Yeah, I'm just, it's the same n, right? But thanks for mentioning. Okay, and okay, so we have this, and now here's how I want to do an encryption. Or here's how I want to do first encoding. To do encoding, I want to first choose a random R of x with, as usual, coefficients in 1, 0, minus 1. And I want to do the following encryption of E of M. I'm going to say that E of M is equal to M of x plus x minus 2 times R of x. Now, R of x, you could make R of x have degree n minus 2, so this doesn't overflow over n, or you could say that it's just random degree n, and you could just reduce this mod f of x as you wish. It doesn't matter. This is E of M. It's this encryption, and to decrypt the decryption of E of M, what do you do is just this, take this thing is just the right-hand side mod x minus 2. Okay. So this happens to be very close to being a ring homomorphism. Actually, it is a ring homomorphism as exactly stated. And what I mean in particular is that E of M1 plus M2 equals E of M1 plus E of M2, and E of M1 times M2 is going to equal to E of M1 times E of M2, and I haven't explained why in the world this should work, and it's also not always going to be true. So I'm just going to say usually, and we'll see exactly what's necessary to make this actually work. Well, suppose that I take an M1 of x, and we take encryption of M1 is going to be the corresponding M1 of x plus an x minus 2 times an R1 of x. The encryption of M2 is going to be this. Then the product of the two E of M1, E of M2 is going to equal, well, what? It's going to be M1 of X multiplied by M2 of X plus X minus 2 times R1 of X, M2 of X, plus R2 of X, M1 of X, plus X minus 2, R1 of X, R2 of X. Okay, so the encryption of this times this is going to be that. And so what's going to happen here, and then what is going to happen here? Well, this operation, this lives in Z mod QZ of X modded out by F of X. So what's going to happen is that if I multiply these two things together, I'm going to get the actual literal product of these things plus this stuff. And what the heck is going to happen with this stuff? Well, where do we go? Okay, so we have R of X times M2 of X. We've got an R2 of X times M1 of X. What's this going to be? This is going to be the actual R of X, the actual multiplication inside of this field. This thing is going to turn out to be the same thing as literally R of X, M2 of X, plus some multiple of F of X. And here's the point where short times short equals short. The fact of the matter is that if I take an R of X, which is short, because I made it trinary like that, multiplied by this, which is also short, what I get is something where the coefficients don't get too big. And here, what is this? You could view this R of X, this thing could be viewed as R of X, M2 of X. And what is that? That's exactly the same as the product of the polynomials plus some multiple of F of X. Now suppose F of X was just a random thing, it was just an arbitrary thing like H. Suppose we were trying to do this with H. If we do this with H, then we've got pretty good, this has got, the coefficients of this will be small mod Q. And if I do something like this, if I'm in X space, coefficients small mod 2, mod Q, small coefficients small. So the whole point is that if I take this and I multiply by this, when the dust clears, there's going to be no reduction mod Q taking place when I multiply a short polynomial M1 by a short polynomial M2, in spite of this padding that happens here. And what if F of X weren't short? If F of X wasn't short, if I tried doing exactly the same thing with the H of X, at this stage, chaos would ensue. At this stage, if the coefficients of F were, if this was H and the coefficients were random mod Q, then when I do this multiplication, the coefficients of this are going to be all over the map mod Q. Yes?
In your original encryption algorithm, so all of this is occurring in the X space?
Yes, I haven't even encrypted anything yet. Actually, I'm just telling you at the moment how to decode encoding. Really, I haven't encrypted. So pardon me. But what I'm telling you about is a special property that's true in X space. True in X space. If in X space, if you take a short polynomial, multiply it by a short polynomial, it's going to stay a short polynomial. Yes.
So this requires, so F is just these random small coefficients, so this means we need Q to be like exponentially large.
Yes. Q will be required. Will certainly be required to be some constant to the n. Hopefully, not a very big constant to the n. I'm hoping that Q doesn't have to get too big, but I haven't pinned down optimal parameters or anything.
So the other question is then what we have here is we've got x minus 2 and some reasonably small coefficient thing of degree less than n.
Right.
But then when you multiply by x minus 2, you get something of degree n, and you need to reduce that further.
You get something degree 2n actually.
Well, I mean, the point is that, so why doesn't reducing mod f change the reduction mod x minus 2 by 1?
I'm not. I'm not. It does change, but I'm not worried about that. Because everything that happens here. What suppose I take something like this. How am I going to let me explain what I was planning on doing for decoding, not decrypting. For decoding, reduce mod Q, then reduce mod x minus 2.
Okay, but we reduce mod f.
And reducing mod f. Well, let's say that we're not reducing anything. Let's say we're just I'm multiplying this, and what I actually mean, I'm multiplying this. This is the m1 times the m2 in the x space. That's equal to the literal product of the polynomials plus other stuff that's multiplied by x minus 2, plus a whole bunch of coefficients in here that might or might not stray over q over 2 or below minus q over 2. What I'm saying is that first of all, no coefficients are going to go above q over 2 or below mod q over 2. Therefore, when you reduce the whole thing mod q, you just have this thing actually as expressed over the integers. We are not reducing mod f anymore. We are reducing. Well, yeah, and yes, we are, because first we reduce mod x2, and then what you end up with is the one thing I didn't tell you with. The result is going to be the original number m1 times m2 mod f of 2. So that's where the f is going to come in. Okay, so you want f of 2 to be big enough so any number you deal with is can be conveniently written mod f of 2. So f is a degree n thing with small coefficients. So it's going to be you just have you have to choose your parameter n. So you want f to be large enough that you could deal with any number you feel like dealing with. Also. What was I about to say? Also, I want f to be secret. Now, if n is 10, that's going to be very hard to keep f secret. So I need f to be whatever minimum I need to get away with to keep the identity of f combinatorially secure. And that's probably going to make a restriction of no. I doubt if I can ever get n under 100 with that condition. But you just what you want to do is you want to have enough coefficients taken from this degree n irreducible mod q. You just want enough of those that you can't find one that you can't pick it out by random choice. Okay, so I haven't done anything. I have just explained how to decrypt the decoding. Now let me actually encrypt. Okay. So what I want to do is I want to encrypt. I take m, I encode that to m of x plus an r of x times an x minus 2. Oh, by the way, I just remembered what I was going to say before. X minus 2 is completely arbitrary. I could also say replace x minus 2 by 3. And I could make, and then all the numbers would come out in z mod 3z to the n, something like that. I kind of like dealing with actual integers, so that's why I'm using x minus 2. So m go to the encryption of m is m of phi of y plus r of phi of y times phi of y minus 2 reduced mod h of y and mod q.
So phi and psi, are they public or are they private?
They're definitely very private. So in other words, F is private, H is public. The isomorphism between, this is the public space, the Y space, and then there's a secret isomorphism given by the phi and the psi that take you into the X space. And F of 2 is public. I mean, it could be public, could not be public, but that simply doesn't matter, I don't think. That's is F of 2, basically. Well, I would like to give away F of 2. I would like my combinatorics to work out so that giving away F of 2 is not giving the vote away.
It seems like you might have expected you have this matrix of determinant of 2.
Yeah, there's no particular reason to reveal F of 2 or not to reveal F of 2. It's certainly the value of F of 2 is only relevant to the encryptor. So it's perfectly possible that you even want to keep it secret. But I hadn't even particularly thought about that. I don't think it should matter much. Yeah. What's that? Only using it to decrypt, right? Yeah, that's the idea. That's why I like using x minus 2. Oh. Yeah, yeah. Good. Isn't F what? Phi is extremely secret. You would not believe how secret Phi is.
So how is someone supposed to do this?
Oh, well, they have to be brilliant, first of all.
This is symmetric or public system?
This is, as described, is in the process of being a symmetric one. But however, it could be translated into a public key version. However, it's not clear if the wonderful advantage of parameters of the shape n associated lattice dimension of degree n squared, whether that gets preserved in the carryover to a public key version.
So we should think of it as a private key.
So for the moment, consider it private. Just consider it a private key. This is lots of thought still going onwards for the best way to turn it into a public key. Okay, and so the point is that if you take m, then you translate it into this. So and this will just, as far as I know, as far as anybody can tell, it would be wonderful to be able to prove this, but the coefficients of this appear to be randomly distributed, look randomly and uniformly distributed, mod q. No proof there. Okay, and so suppose now suppose I were to encrypt a whole bunch of things. Suppose I was to encrypt. And now forget my previous meaning of M1, M2, and now have a completely new meaning. Suppose I want to encrypt M1. Suppose I want to create something C1, which is encryption of one thing. I want to have a C2, which is encryption of M2. Just a whole bunch of these. So clearly, if somebody trying to break the system has no hope until a sequence of messages, unless a collection of messages is there, because H is independent of, there can't be any information contained in H because it doesn't depend upon F. So suppose someone sees a collection of encryptions here, this, what do they know? Well, first of all, how would you break the system? How would you break the system? Well, what you want to do is you need to translate this into some space. This C1 is going to equal, some matrix. Well, C1 is going to equal some matrix times M1. C2 is going to equal the same matrix times M2. CK is going to be equal to the same matrix times MK. There's going to be some n by n matrix with the property that if you apply its inverse, and let's just say that A inverse is equal to B. So there's some n by n matrix B, which is A inverse, with the property that B times C sub I is equal to M sub I for each I. So the attacker trying to decrypt, how can they decrypt? Well, he's got to find some sort of n by n matrix that will take an arbitrarily long list of ciphertexts and map them to an arbitrarily to similar length collection of vectors, all with small coordinates. It's exactly the same problem as, suppose you're given C1, C2 up through CK in one vector space, find a change of coordinates in which your whole list has small coefficients. Make sense? And it seems, and this is where I'm really curious to get opinions, that this is fundamentally a minimally n-squared dimensional lattice reduction problem. Because how are you going to do something like this? Well, you're going to actually take this. You're going to put stuff together. You're going to put stuff together until you get so you can have B. Then you have B times C1, C2 up to CK is equal to M1, M2 up to MK. So you're going to try to find a B such that all these things are small. Now, what is this? This is going to be a K by n matrix. Okay, and I think it's good. Sorry, yeah. K going up that way and n going that way. It seems to me, and if this was a boring sort of slide talk, I would put a completely incomprehensible slide up, which ostensibly, if you read it, showed you a lattice reduction argument involving n-squared dimensions that you have to solve. Why don't we just assume that as far as I can tell, the process of finding some linear transformation B that has the property of sending an arbitrary list of these things to an arbitrarily long collection of short things. I just want to, all I know at the moment is an n-squared dimensional lattice attack on that. And I'm very curious to know if people here could see something better than an n-squared dimensional attack.
So where are you assuming that K is large?
Well, if K isn't as large as n, then you don't even have everything determined. In other words, until K gets to be as big as n, then you pick any list of ciphertexts, you pick any list of images here, and you could find something that's going to satisfy it mod Q. that you can send it to mod q. So you have to have a long enough list to at least have things overdetermined. And the overdetermination doesn't seem to happen until about k is equal to 2 times n squared. Yeah.
If you apply the inverse of this transformation here,
Yeah.
then all of these encryptions turn into small things. And well, if you look at a particular entry of what you have, then that's a linear transformation from the n, like n coefficient thing to the 1 coefficient. And so there's just, you get that 1 coefficient by dotting with some vector, and so there's some vector that's nearly orthogonal to all of your encryptions.
Is somebody following this better than me? I'm not getting that.
I assume all your messages are equal to 1.
So
Oh yeah. Well, right, sure. So, well, but all your messages aren't 1. All your if assume all your messages are 0, then all your messages consist of the random padding of the.
No. I mean, all of your messages, though, when you put them in the x basis, all the coefficients are small.
That's right. Yes.
And so that means, in particular, any given coefficient is small.
Right.
And the coefficient in the x basis is some linear combination of coefficients in the y basis.
That's right.
And so there's some linear combination of the coefficients in the y basis that's always going to be small for any.
Yeah, but what I was just telling Leo was that there's a zillion different solutions like that until you try to accomplish a long enough list simultaneously so that there's a unique solution.
That shouldn't be explored.
I mean, there will be a lot of solutions because each coordinate is such a solution, like sums of coordinates or linear solutions. But I feel like even knowing a few of the solutions to that will like tell you something useful about this app.
But how could it possibly, in the sense that I could write down, I can write down a pretty arbitrary collection of C's and M's that has nothing to do with F's F at all. I mean, they're.
Well, I mean, all I'm saying is that.
I mean, it doesn't.
I mean, all of your encryptions are like low degree linear transformation, like.
No.
Or low sums of low degree multiples of the like.
They're all n degree.
Powers of phi. All of your encryptions are small coefficient combinations of the powers of phi.
Of the power of p. Oh, the powers of phi, but.
I'm going to try and solve for the like space of. I'm going to try and solve for what the powers of phi are. By doing some sort of.
Okay, well, it's perfectly conceivable that you're right. I honestly don't know. That's why I'm talking about it here. I want your opinion. So rather than taking up more time here, why don't we just assume that that you will work at this?
It's actually a good thing to talk about. If we want to have maybe, why don't we have a few more minutes? Because this is kind of what I want, is for people to be attacking and challenging. That's why you're giving the talk.
Yeah, right.
So good. Why don't we do about 5 more minutes on people in the audience to talk to, and then maybe we can.
Yeah, any more meanies out there?
This is the last one, right? That's why you're giving the talk.
That's why I'm giving the talk. I want to be attacked. Honest, really. Imagine myself strolling through Central Park and it's 10 o'clock at night.
In terms of preparing the next few minutes, so you have more to talk about too, or should we just?
No. The only thing I would, if it wasn't clear already why this is a homomorphic system, then I would want to talk more about that. But I think I've gotten that across. I think I've gotten across any essentials that I want to get across, and that's all I wanted.
I suggest that we have maybe 10 minutes more of attacks and talking about it, and then we can sort of break up into people talking more privately about that, and the 5 o'clock will go to the 10 minutes. So how about that? We'll have a sort of a formal 5 to 10 minutes of attacking, and then we can break up into more informal. So continue the conversation with attacking.
Yeah, you first.
Daniel, you want to come up to the board?
Yeah, come on up and.
This will be
Okay, so I mean, all that I'm claiming is, so what's the point? There's
Oh, here, hold on a second. Let me pass this over. Did you see where? Okay, so just hold that.
okay. Okay, am I audible? Okay, so my idea is just that there's some linear transformation which takes, I need another name for a polynomial, which takes g of phi of y to b of x. Oh, okay, so the issue I guess might be that this is only a polynomial here. So, okay, it's not quite clear how latticing this is going to be. But in any case, what we do know is that sort of L of encryption of basically anything has small coefficients. And in particular, this says that if you look at the like L of E of star has a small x to the k coefficient. And this thing, well, I mean, it's a linear transformation, so this is just like we're taking the coefficients of E of star and we're dotting it with V. So what we have is that we've got E of star dotted with some V. I guess maybe mod Q has small coefficients. And there are a bunch of these. I mean, we're going to get one V for every possible K, and also, you know, an extra one for taking plus or minus. And if we take sums of those V's, we'll get other things that satisfy this with slightly lower quality. But essentially, like, these V's corresponding to the X to the K's are presumably, at least heuristically, they're sort of the best solutions to this equation.
Small coefficient, you mean is small, it is itself.
Yeah, is small, sorry. And so I guess this isn't quite a lattice problem. I mean, it's some sort of problem.
I should have mentioned,
Yeah.
if you keep everything linear, it's a lattice problem. You don't have to do it. If you keep everything, if you consider it nonlinearly, you get an extremely weird problem in algebraic geometry. Trying to find the small solutions of really some crazy high-dimensional algebraic varieties. Don't have any idea how to even begin with that. That's why I'm sticking to it.
Yeah, I mean, so okay, I mean, this is, I guess, some kind of learning with errors problem then.
You mean now I learned that I shouldn't be talking to you?
Well, no, I mean, this problem gives you some kind of learning with errors problem. I mean, you want to find some V's such that when you dot it with any encryption and take the answer mod Q, you end up with something small. And if you can find a bunch of those, then at least heuristically, those are going to be the best ones are going to be the coordinates of this function L.
You're kind of talking about what I was talking. You're decomposing my matrix into columns or something like that.
Well, yeah, but my point is that you can solve for this matrix sort of one column at a time.
I don't think so. That's if you
Certainly have to distinguish, for example, between random elements and encryption.
Well, no, but I'm saying, I mean, if you can sort of find all of the solutions to this thing, then those will be more or less the columns of your matrix. And so, but sort of each one of these problems is an n-dimensional problem rather than an n-squared dimensional problem.
right. A whole bunch of times it's turned out to be wrong to think you're going up to an n-squared dimensional space. Like, for example, one of the obvious transitions to putting entry over into matrices and stuff is you apparently end up with an n-squared dimensional problem, but in fact it can be broken up into a whole bunch of little n-dimensional pieces. And I totally agree that if you see a way of breaking this up into n separate n-dimensional problems, then right.
Okay.
I don't have a leg to stand on. The question is, can you actually do that?
Well, I mean, this is heuristic that the V's that you find from this will be sort of the best solutions. And if they're not the best solutions and there's sort of other random solutions that do approximately as well, you might not be able to distinguish which ones come from here and which ones just sort of are random. But I don't think that's going to happen.
I think there is one solution that looks, if you have a long enough list, there'll be precisely one solution. I think you can calculate that with high probability there's only one solution. You can't really narrow your way down.
Yes, but if you don't have the exact right solution and you instead have another one that's reasonably small.
No, we know that we have a bunch of solutions to this problem. I mean, to my version of the problem. Like every column vector of your matrix is going to give you a solution. And those should all be approximately as good.
Well, there certainly is not one square root extension.
Right, but what I'm saying is once you find one column, then looking for it, you essentially have to the transformation from one to the other.
I think it's more complicated than that. No, I mean, the thing that you get is that if you have a vector, if you multiply it by phi of y on one side, that's like equivalent to multiplying by x on the other side. And that, okay, I guess phi of y is some circulant thing, but like you don't know what circulant thing it is. Yeah. Yeah. Yeah, I don't think it's that nice. But I mean, I think that you could probably break it down to solving something like n-dimensional problems. Now, it's not clear to me that these problems are as easy to solve as sort of that problem, because this sounds like it's actually more or less an honest-to-goodness lattice problem, where this is, I've got a bunch of things, I want a vector whose dot product with all of them mod q is small. What? Yeah, but okay. Okay, I guess I haven't thought enough about LWEs to see if it's just a lattice problem, but